These are the second part of notes on stoichiometry. Make sure that you already watched the first one before you watch this. Stoichiometry, of course, is very important to chemistry, the heart of chemistry. It's the quantitative relationship between reactants and products in a chemical reaction. It is the numbers behind chemistry. It might be the accounting of chemistry. Some people don't like to do accounting, but everybody likes to do stoichiometry. Stoichiometric path you must follow, my Padawan. Remember to, first, balance the equation above all else. Number two, determine what? Determine the key to stoichiometry. Determine moles. Moles is the key to unlocking all the numbers. Then use the mole ratio. That's what we got to last time. Then, number four, if you are asked for it, you got to find the grams. How do you find the grams? That's what we're going to see today. Sometimes you have to know the number of particles. I don't tend to emphasize that as much because that is also just as impractical as the moles itself. I like something you can measure on a balance, grams. So I'm going to show you today how to add on to the end and also to the beginning and to convert from grams to grams. The conservation of mass is the underlying law of chemistry laid down by Lavoisier that you cannot violate. The mass of the reactants is equal to the mass of the products in a chemical reaction. What goes in must come out. Nothing new and nothing is lost. That's the conservation of mass. The mole ratio, which we began to use last time, is the only way to jump from one chemical to a different chemical in a stoichiometry problem or in any chemical equation. It's the only way to do it, the mole ratio, which is of course why we balance, and then the coefficients from the balanced equation give you the mole ratio. But what if you don't have the key? What if you don't have moles to begin with? Sometimes you don't have moles. Sometimes you have grams. If you have grams and you have to get from grams to moles, well, how do you do it? You do it using a unit that contains grams and moles, which is the molar mass. The unit of the molar mass is grams per mole. It's really the way to convert between grams and moles. Remember, the molar mass is the mass of 1 mole of a chemical. The only fair way to measure chemicals is with moles, and the molar mass is the way that we measure them. To make sure you have a mole of something, well, you need to know its molar mass. Also, at the end of a problem, when we've gotten moles of a chemical, well, often we want to convert that into something we can actually measure, so we usually want to convert it back to grams. So how do you think you get from moles back to grams? The opposite of what we saw earlier? Well, guess what? The answer is the same thing, the molar mass. So the molar mass will convert you from grams to moles or from moles to grams. Either way, that's the conversion. And so we have to use it quite a lot. Now you can see why I emphasize so much on being able to calculate the molar mass of any chemical. It's the answer to both of these questions. How do you get from grams to moles? How do you get from moles to grams? Both of them are answered molar mass. So of course you've got to know, it's critical that you know how to calculate the molar mass of a chemical. Generally, we round them to the hundredths place because that's about as accurate as our balances are in the lab. And we have to calculate them carefully, but beyond that, it's not too hard to calculate a molar mass. Just add up all the masses of all the constituents of a chemical. Here are two examples where we have to use both the mole ratio and the molar mass. So these are getting a little bit harder. What's the first thing we always do in stoichiometry? Balance. We've got to balance this equation. Let's not do anything until we've balanced it. Well, let's see. 3 hydrogen on the left, 2 on the right. That's odd even. Better double this one. Now, to make the hydrogen the same on both sides, I need to multiply the other one by 3, coefficient of 3 in front of the water. Okay, and now I've thrown off the nitrogen. I've got 2 nitrogen on the left. Let's make 2 on the right. That gives me a total of 5 oxygen on the right, 2 on the left. Better make the odd side even. Okay, and now we've got 12 hydrogen. Oh, so we better make this 4 to make it 12 hydrogen on this side. And then, oh, we've thrown off the nitrogen, fix the nitrogen. Now we've got 10 oxygen on the right. We can get 10 oxygen on the left. Balanced. We've done this one before. This was also the one I did on the video, balancing equations hard. So you can see it there. I was just trying to get that out of the way. Remember, always balance first. Now look at the question. How many grams of water are produced if 1.9 moles of NH3 are combined with excess oxygen? We'll talk about what that means later, but notice excess oxygen doesn't have a number to it, so you can't do too much with that right now. Let's just get to that later. Okay, so we're looking for grams of water. Our answer is going to come out in grams. So we are no longer dealing only with the mole ratio, but what are we given? I know it's kind of cut off from one line to the next, but it says 1.9 moles of NH3. Well, that's the key. Remember, moles is the key to stoichiometry. So we're given the key again. So this problem isn't too bad. And now what do I have to do? Just like in the previous problems, I want to jump between chemicals. I want to jump from ammonia to water. Look at those coefficients. For ammonia, you should know which one is ammonia, and you should know which one is water. From ammonia to water, what are the numbers? There's a 4 and there's a 6, right? So which way do we write it? It's a mole ratio we're going to use now to jump between chemicals. So we need moles over moles. Which number needs to go on the bottom? How about which chemical needs to go on the bottom? Notice, in order to cancel moles of NH3, well, I better have moles of NH3 on the bottom. What number comes along with that? The 4. I've got to have moles of water on the top. What number comes along with that? The 6. That is why we write it this way. This is the mole ratio, just like we did before, converting from ammonia to water. This is why moles is the key, because once you have moles, well, then you can jump around to any other chemical and find the moles of that chemical as well. So 6 over 4, and we don't reduce it. And then when the units cancel, notice I will have moles of water now. Once we've multiplied that, but we're going to do it at the end, but if we multiplied that now, we would already have moles of water. That's the unit that remains. Now, the only problem is I have to get from moles of water to grams of water. So how do I get from moles to grams? Molar mass. The molar mass of water is one that we've calculated before. Oxygen is 16.00 grams per mole. Hydrogen is 1.01 grams per mole. And there's 2 of them. So it adds up to 18.02 grams per mole. That means that's how many grams you need to have 1 mole. But notice, we have moles of water. We have to cancel that unit. So moles needs to go on the bottom, and the grams have to go on the top. And that's where we put the 18.02 grams. You're going to see later that we don't always write molar masses this way. This seems like the normal way to write it, grams over moles, but you can actually write it upside down. We'll talk about that later. Notice which unit cancels now. What unit cancels? Moles of water. It better cancel, because that's not what I'm looking for in my answer. So all the units that you're not looking for had better cancel if you're going to get the right answer. The only unit I'm going to be left with is that last numerator unit, grams of water. That's going to be my answer. So I take 1.9 times 6 divided by 4 times 18.02, and I could divide by 1. Doesn't change anything. Might as well divide by 1. Equals 51.4 grams of water. You could have kept another digit there Often we keep it to the 100th place, that would be fine. I'm just rounding it to the 10th place, mostly for space here. If you kept one more digit after the decimal, that would be fine. Just don't keep more than that. So that would be my answer, and then usually what I want to do is indicate that I know that's my answer by putting like a box around it or a circle around it. Now notice we went from moles of one chemical all the way to grams of a different chemical. Well, that's the same thing we're doing in the next problem, so I'm going to do it a little faster. How many grams of oxygen are required to produce 0.3 moles of water? Okay. So notice in this situation, what's the first step I should do? Oh yeah, balance. But it's the same reaction, so we already balanced it. Just remember, always do that first. And what are we looking for? We're looking for grams of oxygen this time. That's oxygen. And what are we given? Oh, we're given the key again. So again, this is an intermediate problem because we're given the key right at the beginning. And if you notice, 0.3 moles of water. So we've got moles of water. We want to jump to which chemical? Which is the one that's going to be in my answer for this question? It's the oxygen. So I'm going to have moles over moles as my mole ratio to jump between them, the only way to jump. And which chemical goes on the bottom? The water goes on the bottom. So what's the number that comes from the balanced equation? What's the coefficient for water in the balanced equation? 6 goes on the bottom. And then moles of oxygen is going to be on the top. What's the number from the balanced equation for oxygen? 5. So notice, this is my mole ratio for this problem. It's moles over moles, that's why it's a mole ratio. The chemical you're starting with always goes on the bottom. The one you're jumping to always goes on the top. And we don't reduce it. Well, you can't reduce this one anyway, but we would not reduce it. Notice if I cancel units, all that we're left with is moles of oxygen. So now we have the moles of the chemical we want in our answer. The only problem is we have to get from moles to grams. So how do you get from moles to grams? Molar mass. What's the molar mass of oxygen? Is it 16.00 grams per mole? No, that is the molar mass of one oxygen atom. When I say oxygen, I mean O2. So you've got to multiply the 16 times 2, you get 32.00, and then much like in the previous problem, well, since I have to cancel moles, then moles has to go on the bottom, and I wind up with this. This is the molar mass of oxygen. Notice that it's 32.00 grams of oxygen over 1 mole of oxygen. Now notice that's 1 mole of oxygen, even though in the balanced equation there's a coefficient of 5. Molar masses, remember, are the mass of 1 mole, always. So in a molar mass, that will always be a 1, regardless of what the coefficient in the equation is. And then what unit is going to cancel now? Moles of oxygen is going to cancel. After canceling those, the only unit remaining is the unit that's going to go into my answer. I take the 0.3 times 5 divided by 6 times 32.00 divided by 1, and I get my answer. My answer is 8.0 grams of oxygen. Now notice I didn't really have to divide by 1. If there's ever a 1 that you're multiplying or dividing by, I would recommend skipping it, because if you multiply by 1 or divide by 1, you will get the same number you had before. Also, there's a chance you might make some kind of typo on your calculator, so it's just not worth the risk. And then, of course, I probably want to box that answer, or let me just circle this one. I'll circle this answer to show that I know that that's my answer. And then I want to look back. Oh yeah, was that what I was looking for? Question asked for grams of oxygen. This had better be grams, and it better identify the chemical oxygen. So those are intermediate stoichiometry problems. Remember, the mole ratio is the only way to jump from one chemical to another in a stoichiometry problem. It's moles over moles. The one you're starting with goes on the bottom. The one you're jumping to goes on the top. Remember that the molar mass is how we get from grams to moles or moles back to grams. We're going to use that tool in both ways in our final problems, which are the hard kind, the difficult stoichiometry problems. Finally, we get to the real deal, converting from grams to grams. These are the harder stoichiometry problems, and these are the practical ones, because really we can't measure moles, but we can measure grams. So very frequently we have to convert between grams and moles, and then we have to convert from moles back to grams at the end. This is the kind of problem I want you to be good at. This is the kind that we actually have to use practically all the time. So we cannot go directly from grams of one chemical to grams of another. That would be great, but you can't do it because they all have different molar masses. Instead, we have to go through moles. Moles is the only way to fairly treat chemicals because you're counting how many there are in just big groupings of a mole, but you're counting how much is there. So it's being fair to the chemicals. So there's a pattern that we follow in these problems. First of all, of course, we balance the equation. Look at the one on the bottom. You should know this one by now. That is hydrosynthesis. What kind of reaction is that? What reaction type? Combustion. It's a reaction with oxygen. So notice that we're going from grams of one chemical, grams of chemical X on the left. That's where we're starting. And then we're ending up with grams of chemical Y on the right. Well, you can't go directly. You can't just take a skyrocket and go and land there. That would be very easy, but we just can't do it. So we have to find another way to get there. We have to make several transitions. We have to take 3 steps to do this. First of all, we have to convert those grams into moles. That's the only way to be fair. So once we get those grams of chemical Y converted into moles of chemical Y, well, now we've got our key right there. Once we have our key, we can jump around using the mole ratio, and we can get to moles of the chemical we want to know about, the one in our answer. Finally, we have to convert that back to grams because, of course, grams we can actually measure, and that uses a molar mass again. So look at the pattern we have. We start off with grams of chemical X, and we use the molar mass of chemical X right here to convert it into moles. Then once we have moles of chemical X, well then we can use the mole ratio to jump between chemicals. That's the middle step. That's kind of the heart of stoichiometry. That step pretty much always happens in a real stoichiometry problem. Finally, at the end, we want to convert that new chemical back to grams using the molar mass of chemical Y. So notice it's a 3-step problem. We use a molar mass first, then we use the mole ratio in the middle, and then we use a different molar mass at the end. This is the pattern you're going to see in most stoichiometry problems, the real ones, going from grams to grams. Here is an example of converting from grams to grams. Remember this equation, hydrosynthesis? Oh yeah, well there's 2 oxygen on the left and only 1 on the right. I better double that. Then that gives me 4 hydrogen. Well, I better double that. And oh, that's balanced. Good. A lot of equations, of course, are that easy to balance. The question is, how many grams of water are produced from 6.0 grams of oxygen? Well, do I have my key? No. I'm starting out with grams of a chemical. So this is the first time where we're not starting out with our key. We have to make a key. We have to go to the hardware store and make it a key. So the way that we make a key is we convert grams to moles. How do you get from grams to moles? Molar mass. What's the molar mass of oxygen? You should know it now. 32.00. But look at what I'm starting with. I'm starting with grams of oxygen. Right there, grams of oxygen. So that's the unit that I need to cancel. That means grams of oxygen has got to go in the denominator of my term. Interesting. So in a way, this is kind of like writing the molar mass upside down. Technically, this is still the molar mass. Some people think of this as dividing by the molar mass, but it's really the molar mass because 1 mole of oxygen is the same thing as 32 grams of oxygen. They're both a mole of oxygen. So you could actually write it either way. But notice this is grams on the bottom. I like to call this grams on the bottom. This is the first time we've seen this because we're starting with grams now. So grams have got to cancel, and then we're going to have our key, moles of oxygen. Once we've got the moles of oxygen, of course, now we can jump around. What's the chemical we want to jump to? Water. We're jumping to water. So oxygen is going to go on the bottom, water is going to go on the top. What's the coefficient that goes along with the oxygen? It's an invisible 1. Notice there's no coefficient up there. It's an invisible 1. What's the coefficient that goes along with water? It's a 2. Well, that goes on the top. Notice that the mole ratio is moles over moles. It's moles over moles. And whichever chemical you're starting with goes on the bottom. Whichever chemical you're jumping to goes on the top. Then, of course, this unit cancels. And now we've got the right chemical. We've got moles of water. How do I get from moles to grams? I need the molar mass. The molar mass of water, we already said, was 18.02 grams per mole. So which of those units do I need on the bottom now? I need to cancel moles of water. So the moles are going to go on the bottom. How many moles? It's a molar mass. So it's 1 mole. Remember, molar masses are always 1 mole. Notice on the left we see that there was 1 mole, and on the right we see it's 1 mole. Even though the coefficient for water is 2, that doesn't affect the 1 that's in a molar mass. It only affects these coefficients over here in the mole ratio. Those are really that's the only time you really use the ones from the equation. Otherwise, it's always 1. And then what unit will cancel now? Moles of water will cancel. So then I'll be left with the unit I want in my answer. Look at the question, grams of water, that better be. And so we take the 6. Let's skip the 1s this time. So 6 divided by 32 times 2 times 18.02. And you get grams of water. How many grams? 6.85 grams of water is the answer. And then I probably want to make sure that everybody knows that's my answer and circle it. And I want to double check, yes, that's what I was looking for. So notice we can skip all those 1s because times 1 doesn't change a number, divided by 1 doesn't change a number. That made it a little bit quicker, okay? And I have to be very careful with each step, multiplying and dividing, very careful, okay, when I'm with my calculator or doing it on paper to get the right answer. So that's how you do a harder stoichiometry problem. I'm going to do another example a little bit faster. I'm going to do this one a little bit faster, so try to keep up with this. Now, what's the first thing you always do in a stoichiometry problem? Balance. We've balanced this one before, so I'm just going to throw the coefficients in. You can double check, make sure it's balanced. Yes, it is balanced. Now, how many grams of hydrogen, that's hydrogen, are produced from 12.0 grams of water? Well, I've got the grams of water to start with. Is that my key? No, I've got to make it a key. To go from grams to moles, how do you get from grams to moles? Molar mass. What's the molar mass of water? 18.02 grams per mole. You can calculate that pretty quickly with the periodic table. Do the grams go top or bottom? Oh, notice, again, the grams go on the bottom. Isn't it funny that at the beginning of a stoichiometry problem, grams seem to always wind up on the bottom? Of course they do, because you're starting with grams, and we have to cancel that. So you can only cancel it by dividing. Now we've got our key, we've got moles of something, this is moles of water. But moles of water is not what I need in my answer. I need moles of hydrogen, which is on the other side, on the product side. So how do you jump between chemicals? Mole ratio. It's going to be moles over moles. Which chemical goes on the bottom? Water. What's the number that comes with the water? 2. And which chemical is going to go on the top? Hydrogen, moles of hydrogen. What's the number that comes with the hydrogen? Invisible 1. This is the mole ratio that we're going to use in this problem. 1 over 2, because we're jumping from the water to the hydrogen. That's the way you put it. And then what unit is going to cancel? Moles of water. Now we've got moles of hydrogen. Notice we've got moles of a different chemical now. That's the chemical we want in our answer. But in order to get to the final answer, I have to convert that back to grams. How do you get from moles to grams? Molar mass. So I need the molar mass of hydrogen, and remember, when I say hydrogen, I mean H2. So one hydrogen atom is 1.01 gram per mole, times 2 is 2.02. Do the grams go top or bottom? Look what has to go on the bottom in the next term. It has to be moles of hydrogen on the bottom. So that means the grams have to go on the top. That is the molar mass of hydrogen. So notice that the molar mass I wrote on the right side seems to be what we would call sort of right side up, maybe, with grams on the top. The one I used at the beginning was sort of upside down with grams on the bottom. Okay? Those are both molar masses of two different chemicals. And then, of course, what unit is going to cancel? Moles of hydrogen is going to cancel. Let me just erase those circles. And then if I want to get through to my answer, I start off with 12.0. I divide it by 18.02. I divide that by 2. Then I multiply by 2.02, and I wind up with my answer. What is the unit of my answer going to be? Grams of hydrogen, it better be. And what's the number of my answer going to be? 0.69 grams of hydrogen. So it's funny that using 12 grams of water only gives you that tiny little bit of hydrogen, 0.69. That's because hydrogen is the lightest element in the universe. It has the lowest molar mass for any chemical. So hydrogen is underrepresented in grams. This is a good example of why we have to use moles, because grams are not fair to hydrogen. They don't count it correctly because it's such a lightweight atom and such a lightweight molecule. Okay, so that's the second example of converting from grams to grams. My last example on these notes are going to be one that uses that equation that we've solved before. It's the one that we did it earlier. Let's do it really quickly. Let's see, we've got 3 hydrogen on the left and 2 hydrogen on the right. So I want to make the odd side even, and then I want to make the hydrogen match. And then I want to fix the nitrogen, and then that's 5 oxygen on the right, 2 on the left, make the odd side even. Okay, and then that messes up the hydrogen, fix the hydrogen. Oh, that messes up the nitrogen, fix the nitrogen. 10 oxygen on the right, 2 on the left, times 5, boom. So remember, you've got to remember how to balance equations. And this is a particularly hard one, but if you can balance this, you're fine with, no matter what I throw at you, you'll be able to handle it. So it says how many grams of NO, nitric oxide, is produced from 12 grams of oxygen combined with excess ammonia. Again, I'm going to skirt that issue until the next notes. Excess ammonia just means there's plenty of ammonia. And again, we don't really want to burn ammonia. This is combustion of ammonia. We'll get back to that in the next notes if you're wondering. But again, there's no quantity for the ammonia. So what can you do with that? Not much. So the only quantity I'm given is the 12 grams of oxygen. Well, obviously, that's where I'm going to start. We're looking for the grams of NO. We're starting with the grams of oxygen. So how do I get from grams to moles? I need the molar mass of oxygen. You know it by now, I hope. The molar mass of oxygen is 32.00. We know those are zeros, so we still write them. Does the grams go top or bottom? The grams go on the bottom because we have to cancel grams. And now I have my key right there. I have moles of oxygen. Okay. To get from moles of oxygen to moles of, what's the other chemical? Oh yeah, NO. I need the mole ratio. It's going to be moles over moles. We're jumping from oxygen, so where does the oxygen go? On the bottom. Okay, also you can see to cancel that unit, moles of oxygen has to be on the bottom. And we're jumping to nitric oxide, NO. So where does that have to go? On the top. So what's the number that comes along with the oxygen for the bottom? It's a 5. What's the number that comes along with the NO that go for the nitric oxide? That goes on the top. That's a 4. Look at the equation at the top. Boom. That is the mole ratio that I'm using in this equation. And then what's going to cancel? Moles of oxygen. So now I've got the moles of the correct chemical. Now I've got to get from moles to grams. How do you get from moles to grams? Molar mass. The molar mass of nitric oxide is pretty easy. There's not even any subscripts except for invisible ones. So you've got one nitrogen and one oxygen. So just add the 16.00 from oxygen to the 14.01 from nitrogen, and you get 30.01. Very easy molar mass. But do the grams go on the top or the bottom? What unit has to go on the bottom? Think about it. The unit that has to go on the bottom is moles of NO. So that means that the grams have to go on top. And notice again, at the end of a problem, grams are on top. So what's going to cancel? Moles of NO. And finally, if I go through this three-step process, 12 grams of oxygen divided by 32.00 times 4 divided by 5 times 30.01 gives me, what's the unit of my answer going to be? The only unit that's left that isn't canceled. The last numerator unit is the only one that will not cancel, grams of NO. And what I get is 9.0 grams of NO. So if you can do a problem like that, you're pretty good. That's what I need you to be able to do. You need to know how to balance. You need to know how to calculate the molar masses, when to use them, which way to show them, and how to set up the mole ratio. If you can do that, it's the same pattern on all of the harder stoichiometry problems. So you're going to have some practice working on these. We'll be using these quite a bit. I'm leaving you with a bell ringer. Write the quantities of ingredients you would need to make a sandwich, like a chemical reaction where the ingredients make a sandwich is the product. Determine how many sandwiches you could make from 24 slices of bread. Calculate how much of each other ingredient you would need to make those sandwiches. This is very much like stoichiometry. If you want to make sandwiches out of 24 slices of bread, you need to know how many you can make. It may seem obvious, but then the other ingredients follow along from that using what we call the mole ratio. You would never make a mole of sandwiches, but we'll talk about this in the next notes, the bell ringer.